Any star will run out of fuel in its core, and it starts changing, it starts bloating.
And it begins transforming. It starts drifting and getting so enormous that it will engulf the orbits of Mercury and Venus, coming exceptionally close to Earth. So, imagine looking into the horizon, where the sunrise occupies a significant portion of the sky. Music. Brian Cox, eminent physicist and science communicator, has issued a chilling warning about a baffling phenomenon surrounding Betelgeuse, the star most popularly known as Alpha Orionis. According to Cox, recent observations have revealed a curious dimming in the star's brightness, an event that could signal something truly strange occurring deep in the core of this massive celestial body. But what is causing Betelgeuse's unusual behavior? Could this dimming be a prelude to the star's final moments before it goes supernova? Or is it just another cosmic mystery waiting to be unraveled? Stay with me as we delve deeper into the secrets of the universe. A star in turmoil. When it comes to celestial bodies, size matters, and Betelgeuse is a titan among stars. Betelgeuse, a strikingly ruddy star, isn't your typical celestial object. Its brightness fluctuates between +0.0 and +1.6, making it the most luminous first-magnitude star in the night sky. Here's the kicker. It's not just Betelgeuse's luminosity that stands out, it's also its size. The massive size of Betelgeuse is truly mind-blowing. If it were to replace our Sun at the center of our solar system, its radius would extend far beyond the orbits of Mercury, Venus, Earth, and Mars, reaching well into the asteroid belt. To put its epic dimensions into perspective, consider this. If our Sun were reduced to the size of a ping-pong ball, Betelgeuse would be a colossal structure akin to a football stadium. Let that sink in for a moment. Mass and distance. Betelgeuse's mass fluctuates, but it is estimated to be between slightly under 10 and a little over 20 times that of our Sun regarding its distance. Pinning it down precisely has been tricky. Estimates suggest it's between 400 and 600 light-years away. A significant range. At less than 10 million years old, Betelgeuse is a cosmic adolescent. However, don't let its youth fool you. It has matured rapidly due to its immense mass. Scientists predict it will meet its spectacular finale with a supernova explosion, likely within the next 100,000 years. When that happens, brace yourself. Betelgeuse will shine as brightly as a half-moon for more than 3 months. But here's the reassuring part. Earth will remain safe. Star in motion. Betelgeuse isn't one to linger. It's a runaway star ejected from its cozy birthplace in the Orion OB1 association, the same region as Orion's belt stars. It's hurtling through the interstellar medium at an astounding speed of 30 kilometers per second, leaving behind a bow shock over 4 light-years wide. Back in 1920, Betelgeuse earned another title, the first extrasolar star whose photosphere size was measured. Since then, astronomers have been busy studying its apparent size, which ranges from 0.042 to 0.056 arcseconds. Why the range? Blame it on Betelgeuse's quirks. It's not perfectly round, and its appearance varies at different wavelengths. The surrounding envelope. Betelgeuse is not alone out there. It's surrounded by a sprawling, uneven envelope more than 300 times the size of the star itself. This envelope results from Betelgeuse shedding mass over time, creating a captivating celestial spectacle. Betelgeuse's apparent diameter as seen from Earth is surpassed only by a few other stars, like our Doradus and, you guessed it, our very own Sunday. But there's more to uncover about this enigmatic star. Cosmic characteristics. Betelgeuse isn't just any old star. It's a behemoth in the cosmic arena. Classified as an M1-2 Ia-bred supergiant, this designation reveals much about its nature. The M signifies its red hue and relatively cool temperature, while Ia denotes its intermediate luminosity, placing it between a typical supergiant and a hypergiant. Since 1943, Betelgeuse's spectral fingerprint has been a constant reference point for astronomers studying other stars. Pinpointing its exact luminosity is no easy task due to uncertainties surrounding its surface temperature, diameter, and distance. Yet again, the 1960s denoted a defining moment in how we might interpret the heavenly convection hypothesis because of 2 key improvements. First, the stratoscope project took off in the United States. As balloon-borne telescopes rose above Earth's atmospheric turbulence, these pioneering missions yielded stunning images of solar granules and sunspots, providing substantial evidence of convection in the solar atmosphere. Simultaneously, the publication of Structure and Evolution of the Stars in 1958, authored by Martin Schwarzschild and Richard Harm, sparked a revolution in stellar modeling. Their work laid the foundation for applying computer technologies to create more precise stellar models, pushing our understanding of celestial phenomena forward. The 1970s brought another era of astronomical imaging technology, led by Antoine Labourie's groundbreaking invention of speckle interferometry. This innovative technique revolutionized ground-based telescope resolution, overcoming the blurring effects of atmospheric disturbance to provide sharper images of celestial objects. With these advancements, astronomers turned their gaze toward Betelgeuse, using infrared telescopes at mountain peaks like Mount Wilson, Mount Locke, and Mauna Kea in Hawaii. They peered through the veil of interstellar dust and revealed intricate circumstellar shells surrounding the red supergiant, hinting at the presence of massive gas bubbles fueled by convection. However, it wasn't until the late 1980s and early 1990s that a breakthrough occurred in visible light and infrared imaging of Betelgeuse. Aperture masking interferometry, pioneered by G. E. Baldwin and colleagues at the Cavendish Astrophysics Group, emerged as a game-changer. This innovative method used a small mask with multiple openings in the telescope's pupil plane, effectively transforming the aperture into an improvised interferometric array. The result: unprecedented precision in measuring Betelgeuse's properties, coupled with the discovery of bright spots dotting its photosphere. These groundbreaking observations, captured by ground-based interferometers, and later refined by instruments like the COST telescope, revealed Betelgeuse's stellar surface in remarkable detail. The emergence of bright patches, or hotspots, on Betelgeuse's photosphere lent credibility to Schwarzschild's decades-old hypothesis of massive convection cells dominating the star's surface. These findings represented a significant milestone in our quest to decode the mysteries of stellar convection, shedding light on the dynamic processes shaping the universe. In 1995, a pivotal moment in stellar observation occurred when the Hubble Space Telescope's Faint Object Camera captured a brilliant image of Betelgeuse with unparalleled resolution. This marked the first conventional telescope image, or direct image, as named by NASA, revealing the star's disk in extraordinary detail. Unlike ground-based interferometers, space telescopes like Hubble bypass Earth's atmosphere to capture images in ultraviolet frequencies. This groundbreaking image revealed a bright spot in Betelgeuse's southwestern quadrant, highlighting a region significantly hotter than its surface. Subsequent ultraviolet spectra from the GHRS, Goddard High Resolution Spectrograph, hinted at the presence of a hotspot near one of Betelgeuse's rotational poles, suggesting an inclination of approximately 20 degrees to Earth's direction and a position angle from celestial north of around 55 degrees. Betelgeuse's unusual behavior didn't stop there. In late 2019 and early 2020, astronomers were perplexed by the dramatic dimming of the star, the first observed in over a century. At its nadir, Betelgeuse even appeared fainter than Bellatrix, Orion's third brightest star. This event, known as the Great Dimming, sent shockwaves through the astronomical community, prompting intense investigation into the star's puzzling behavior. By August 2020, extensive studies, particularly using ultraviolet observations from the Hubble Space Telescope, provided insights into the mysterious dimming. Astronomers suggested that a massive ejection of extremely hot material had occurred, forming a dense dust cloud that partially obscured Betelgeuse's surface. Hubble's observations in September, October, and November offered tantalizing glimpses of markings of heated material traversing the star's atmosphere. This phenomenon culminated in a more pronounced dimming observed by several telescopes in December 2020 and the following months. As Betelgeuse's dimming saga unfolded, astronomers and enthusiasts alike watched with bated breath. By January 2020, the star had dimmed significantly, its brightness dropping from a magnitude of 0.5 to 1.5, a factor of approximately 2.5. In February, reports confirmed Betelgeuse's record low brightness of magnitude plus 1.614, marking it as the least luminous and coolest in 25 years of study. This remarkable dimming captivated both the astronomical community and the public, with Astronomy magazine naming it a mysterious dimming. Speculation ran wild, with popular media and public opinion suggesting that Betelgeuse might be on the brink of a supernova explosion. Although astronomers were quick to remind everyone that such an event was unlikely for at least the next 100,000 years, February offered some hope. By February 22, signs emerged that Betelgeuse's dimming might have ceased altogether, signaling the end of the episode.